Welcome you all to this course on electron diffraction and imaging. So far in the last few classes we have revised what has been covered about electron microscopy, the basic construction of the microscope, its principle of operation, various modes in which the microscope could be operated like diffraction, imaging and spectroscopy techniques. In fact, to characterize a material we require all these three aspects. The diffraction is one which is required to get information about the crystal structure. The imaging is one which we use to get information about the microstructure. The associated spectroscopy techniques could be used to get composition of the material. As I had mentioned in the first class, we can say that the microstructural characterization is complete when we can get information about crystal structure, then composition, then about microstructure. So the diffraction is the one which gives information about the crystal structure. Then the question which arises is that what is the information which we seek for about the crystal structure? There are some informations which we require. What are the types of this field where the crystal structure is classified, what are the various types in which we can have, this is called as the crystallography. So what is crystallography? Crystallography is nothing but study of arrangement of atoms or molecules or motifs in 1 dimension or 2 dimension or 3 dimension, various dimensions which we can have. So what does this crystallography study gives information? It essentially tells, given a motif, what are the possible choices of crystal structures which it can have. That possible choices it tells, but it never tells. Suppose I have given a particular type of an atom, what is the type of a crystal structure that specific atom will take, that it does not talk about. But what are the possibilities which are available to it? These are all the only possibilities which are there, only one of the structures which it can form. That is what this crystallography tells. So that is why this is also called as geometrical crystallography. The energetics of it, what is the energy which will be gained, which it goes to a particular crystal structure, that decides which crystal structure, which element or combination of elements will take in actual practice. Then what for we require this sort of an information? That is the geometrical crystallography, because suppose we are given a motif, there are various fields in which we require this information. One example which we can take of is this wall design. You are given a tile which is a motif, how we can arrange it so that different types of designs could be generated. In the case of a floor design, that is required. Then in the case of textiles, we require this sort of information. Similarly, the same type of information is required in the arrangement of atoms or building blocks of materials or crystals. These are all the areas. Then the next question which comes is that can we have an infinite number of arrangements, or whether there is some limit on it? Yes, there is some limit on it. All these things which I have gone through, but what I will do is I am just briefly touch upon some aspects of it which I feel one should remember. I am not going through all, or I am not telling that this is important. What I feel which one should always have some information at his fingertips. Here what I am trying to show is some various types of designs. This is from a wrapping paper, another is from a cloth, another is which I have taken from a cloth which is put on a sofa. Each one of them, if you look at it, each looks totally different. It has is there something which is common between all of them? Yes, there is something which is common. What is it which is common? The common part of it here is essentially in this is the pattern which gets repeated. and if you keep that pattern adjacent to each other, this whole design could be generated. Here again this is a pattern, here there is another pattern which gets repeated. Okay. Here I am just marking each of these patterns. This pattern itself has got fourfold symmetry. So I do not talk about symmetry, which I will talk little bit later, but as such, since you have studied, you know what a symmetry is, fourfold rotational symmetry. Here also fourfold. If you look carefully, here it does not have any symmetry, okay, though it looks, but if you look carefully it is not. So if you wanted to find out what is the underlying lattice or symmetry which is associated with it, the best way is that represent each of them by a point and then try to generate a structure. This is that structure which we call it as the lattice. Lattice is nothing but each pattern or a motif which gets repeated, that we represent it by a point, and all of them have got a square type of a unit cell which is there in a two-dimensional lattice, correct. So this is what essentially the lattice. On this lattice, when we put the different types of motifs, we generate crystals. So the number of lattices, they are finite and the base of symmetry are, but depending upon the number of motifs which we can have, asymmetric motifs, infinite. So we can construct an infinite crystals, but if you look at what is the symmetry associated, they will fall into some groups, a finite group. That is what we see in real practice. Okay. This is another example. Okay. So this pattern here is essentially a pattern which gets repeated. Okay. Here we can use an asymmetric motif, like a letter could be used or some geometric object. All these things could be represented by a lattice. When we wanted to represent this by a mathematical formula, we use a formula like vector R equals U into A plus V into B plus W into C. This A, B, C are the different coordinates of the unit cell in 3 dimensions. Okay, U, V, W are integers. Okay, once we know these integer values, the entire lattice would be generated, correct. And what we considered is a lattice which is an one-dimensional lattice. So how many types of one-dimensional lattice? Only one type. Okay, it is essentially with some period we can have atoms which can be arranged. Suppose we wanted to construct a two-dimensional lattice, there are many ways in which this could be done. That is, the same lattice, you keep it, okay, up or down at some particular distance, okay, periodically, and at some particular positions. Okay, if I keep it like this, then like this, keeping it, we can generate a two-dimensional lattice. Okay. So how many two-dimensional lattices which we can generate if we go on keeping it like this? Okay. There also there are restrictions. Okay. This restriction comes from the symmetry which is associated with it. So there are only 5 types of two-dimensional lattices can be constructed, which we have already studied. These 5 types of, one is a parallelogram, another is a rectangle, and another is a rectangle, centered rectangle, which is nothing but essentially a diamond. Okay. Then we can have a square lattice, okay, and then we can have a hexagonal lattice. So these are all the 5 types of these 5 types of geometrical figures which we can have, or the unit cells which we can have. This is also based on the type of symmetry which are associated with these two-dimensional lattices. Okay. Okay. Now, if we keep these two-dimensional lattices one on top of the other, okay, at some regular intervals, at some specific positions, we can shift it around. One lattice is there, another you can shift at different positions. Then if we do that, we can generate, in principle, a large number of lattices could be generated. Okay. That is what essentially is being shown here. This is essentially a parallelogram. By keeping another parallelogram but not on top, slightly away, then we can generate a triclinic structure. If we keep it right on top, but the parameters, the C parameter is not the same as A or B, then we can generate a primitive monoclinic. or if we keep one lattice here, okay, then another at a shifter, and then the next one if we try to keep it, then what we can do it is now we can generate a body centered monoclinic. Okay. Like this, keeping one on top, so many lattices combinations we can generate it. But if we look at all of them, what sort of symmetries which are associated with it, then we will see that there are only 14 Bravais lattices are there, 3-dimensional lattices are possible. So, though infinite number of lattices which we can consider, from the symmetry point of view only 14 are going to be there, and this is divided into some subclasses like triclinic, monoclinic, orthorhombic, okay, tetragonal, cubic, trigonal, hexagonal. These are all based on what is the type of again and the base of minimum symmetry which is available. So, everything is based on the symmetry principle is being employed to give this classification to a crystal structure. Then within them there are some subgroups are possible, because the lattice translation vectors will not be able to generate some of the lattice points inside the crystal. Okay. So, that is why they are called as primitive, body centered, face centered, okay, rhombohedral, or A, B or C face centered, this sort of crystal structure. So, in short, as far as the lattices are concerned, we can have only one lattice in one dimension, one-dimensional lattice periodicity. Two-dimensional lattices, if we consider, there are 5 types, and in 3 dimensions we can have 14 lattices which are possible. Okay. Okay. Now, if you look at these lattices, we said that these are based on, these classifications are based on some symmetry elements associated with it. Okay. These symmetry elements are given in this table. The cubic, essentially the minimum symmetry which should have 4 3-fold axis inclined at an angle of 109.47. Similarly, tetragonal has got 1 4-fold rotation. Okay. This minimum symmetry which is necessary, that is how we define that particular class or system, and then the maximum one which tells what is the maximum symmetry which the lattice can have. Okay. Here we are only giving a classification with respect to the minimum symmetry. Okay. Triclinic will not have any symmetry, monoclinic will have 1 rotation axis. Okay. Once this sort of a symmetry element has been fixed, automatically the other factors come. What is going to be the angle? Okay, because symmetry essentially involves rotation or a translation, okay, or a mirror. So, that immediately tells what is going to be the translation vectors. So, that is why we say that A equals B equals C, or A not equal to B not equal to C, angle alpha, beta, gamma. So, this comes from these symmetry elements. Okay. Okay. So, when we talk of symmetry, what do we understand about symmetry? Symmetry is nothing but, in a mathematical term, we can say that there is a mathematical operation which we perform. After the operation has been performed, we find that the function remains the same. Or physically, if we see an object like this particular one, okay, I do an operation of a rotation from here. If I rotate it by 90 degree, it will come like this around an axis perpendicular to this plane. But if you look at it, before operation, the operation of rotation and after, we cannot differentiate between whether this operation it has undergone or not. They look identical surroundings. So, this is what we mean by a symmetry, and symmetry is inherent in nature, okay, and the symmetry is the one which makes us spend minimum energy. Okay. In copying is a form of symmetry. So that only one person has to spend effort, others can just capitalize it. Okay. Like if I take this particular ball, this ball can have an infinite symmetry. If I rotate it at any angle, okay, you cannot differentiate between the previous position and the present position. So we say that it has got an infinite symmetry associated with it. Okay. Now the next question comes, what all types of symmetry elements which we can have in a material? One is called as a translational symmetry. What is translational symmetry? If I move and in a lattice we define as one which has got size in infinite in all dimensions. Okay. We assume that lattice does not have a surface. Okay. So, if I move from this point to this point, it comes to a point which is identical to it. So, essentially these points, by doing this operation, we are not able to differentiate between the previous position and the present position. So, we say that it has got a translational symmetry which is associated with it. Similarly, suppose I take an axis, okay, perpendicular to it, and then give some rotation to it. By doing that rotation, if a lattice point has been moved to coincide with another lattice point, you find that the lattice remains invariant. Then we say that this has got a rotational symmetry which is associated with it. Similarly, we can have a reflection symmetry which is associated with it. Like for example, if you consider this one dimensional lattice, if I take this particular plane midway between this, then this point gets reflected. If I put a mirror, this point gets reflected and comes to identical position. By doing this mirror operation, we can find that again points are all, we are not able to differentiate. Okay, so we say that it has got a reflection symmetry. Similarly, an inversion symmetry, around a point, if one point is there, okay, just you invert it across the origin, and if another point exists, then doing the inversion operation, it comes to a position which is identical. So, we are not able to differentiate it, then we say it has got an inversion symmetry. So, all these symmetry elements which we have talked about are with respect to, okay, essentially an axis or a plane or a point. But what is essentially important is that only condition which we tell is that it should be consistent with the lattice which we consider. We are not invoked the translation, but we said that by doing that operation it comes to a position which is identical with the original position. So, that is why we always say that these ones which are consistent with the translation, we call them as point group symmetry. Okay. So, if all these symmetry elements, okay, cut, intersect, at least there is one point which will be invariant. All other points can undergo some movement, that point will not, that is why it is called as a point group symmetry. Okay. Is there any other type of a symmetry element which is possible? That is, since these are all the translation symmetry is associated with it, okay. Suppose I have a symmetry which is associated with it, along with this I include a translation symmetry, whatever the symmetry associated, it will be moved to this point. So, this rotation or mirror plus this, okay, inversion, add to it a translation that shifts it, correct. Similarly, we can have another type of a symmetry which is possible, is which we are not considered, is what is called as a screw axis. That is, if we consider a staircase, okay, a circular staircase which rotates like this and moves. Okay. Suppose we start from this particular point, after every step when we take the staircase, the step is displaced, but it is lifted up. The same type of a step which is being created. So, it moves like this, and at some particular number of steps, number of small rotation and a step, it comes back. So, this is a combination of translation plus a rotation which is being given. But in crystallography, the condition which is being put is that not any rotation which you can have, if it has to be consistent with the lattice which is given, then the number of rotations which are possible, only that much number of rotations can be given here as well. So, what it will happen is that decides how much is going to be the translation plus a rotation. This is called as a screw. So, screw axis is one which one can have, okay, which essentially a rotation plus a translation. Similarly, another one which we can have is a glide. Glide is essentially a mirror operation, then a shift one side, then again a mirror operation shift it. Okay. Here again it is one of the point group operation plus a translation. Okay. That is how these symmetry elements are coming. Okay. So, space group is essentially, as I had mentioned, all these symmetry operations are there, but along with that there is a translation, then only a lattice will be generated, right. Okay. So, I had mentioned that only translational symmetry, that is one. Rotational symmetry, what we can consider it is that around any point like what is being shown here, if we take a motif, rotate it by some angle, that we can divide 360 by angle, if it gives a number n, okay, then it just a rotation is possible, but this rotation is not going to be consistent. Like here, if some particular angle by which, suppose I rotate it by 90 degree, this point will come here, this is not a lattice point. So, that is why these sort of translations are not permitted. So, that specifies for each type of a lattice which we consider, only some particular types of rotation is possible. Okay. So, that is one type of a symmetry. Mirror I had mentioned, inversion, and this can be represented in various ways. One is with respect to coordinates of this position. So, from one coordinate to another coordinate, if the coordinate changes by this transformation, then what is the matrix which we have to use, that is also a way in which we can represent it. This can be represented in stereogram. There are so many ways in which it could be represented. All these aspects have been covered in the class. Okay. Then another important thing which you should remember is that the rotation is one which brings, if an object is right handed, like for example here, this r when it is written, this is always brought to r which is a right handed one. If an operation of a mirror is involved, a right hand object is made into a left hand object. Okay. That will always be there in the crystal. Why I am mentioning it is that these types of transformation, that is, if you have got only a rotation is involved, then we can have a crystal where one particular type of a molecule, it only has a right hand type, and another which has left hand type which moves. So, these are called as optically active materials. One will give a right hand shift, another will give a left hand shift. So, understanding this sort of symmetry, when we understand, we can talk about what sort of properties which the material will exhibit, or if we know about what type of properties which a material exhibit, we can tell what is the sort of symmetry elements which the material will have. Okay. That makes life simpler in getting information about the crystal structures. Okay. These aspects have all been covered. Okay. Just for the sake of continuity, I had included this slide, but you can go through these, okay, get all the information. This is for the inversion symmetry. So, essentially the x, y, z goes into minus x minus y minus z. Okay. Similarly, the screw axis, as I had mentioned, here you can make out that this is like a staircase, okay, around a point. Okay. From here, okay, you give a translation and then give a rotation, then again a translation and rotation. By doing this point you find that after 6-fold operation it comes here. Okay. This is what essentially a screw axis is. Similarly, glide I had explained, but there are different symbols which are used to explain different types of glides along different directions in the lattice. All these details have been covered in the class. Okay. So, essentially, if you look at what all types of symmetry operations we can have in different dimensions, okay, having just briefly mentioned about the different types of symmetry elements, if we take an one dimensional lattice, the symmetry elements which we can have is one fold. That is, if I take this particular one, okay, lattice, one dimensional lattice, I give an one fold rotation around any point, it will come back to its original position, or around this point if I give a two-fold rotation it will come back, or if I put a mirror here I can have. So, these are all the only symmetry operations which are possible. around a point. So, the point group symmetry operations are only these. Okay. In two-dimensional lattice, if we consider, we can have one-fold, two-fold, three-fold, four-fold, six-fold and a mirror. Okay. What are symmetry operations which we can have as far as three-dimensional lattice is concerned? Here we can have 1, 2, 3, 4, 6, mirror, inversion, and then 1 bar, 2 bar, 3 bar, 4 bar, 6 bar. These operations, as I had explained in the class, is essentially nothing but a rotation and an inversion, which is that completes one operation. Okay. And their combination of these operations are possible. If we consider this sort of a combination, how many types of point groups which are possible? In one dimension, there can be 5. In 2 dimensions, we can have 10 point groups are possible. In 3 dimensions, if we consider, we can have 32 distinct point groups are possible. But if you take the combinations of this, the combinations will be quite a lot. Here for the 3 dimension, it can be more than 1000. But finally, from the symmetry, when we consider, only 32 distinct point groups are possible. Okay. Let us take the space group. So, here also I had mentioned, like point group, it is essentially, as I mentioned, consistent with translation, but it is not translation is added. But in space group, it is a point group plus a translation which has to be there. Okay. Both are there together. In this, if we consider a one-dimensional lattice point group, then one more, all the point groups which you have considered plus one will come, which is called as a glide. Then the total number of space groups which we can have is 7. Similarly, in two-dimensional lattice, if we consider point group, okay, which are 10 plus the glide also will come, then the total number of distinct space groups which we can have is 17. Three-dimensional lattice, if we consider, then we can have the 32 point groups plus, in addition to it, screw and glide also will come. Okay. If all these symmetry operations, okay, if they are operating on a lattice, okay, then we can have 230 distinct space groups are possible. These are all the structures to which, okay, periodic crystals can form or crystallize into. Okay. Okay. If we consider an example in one-dimensional crystal, I had just shown this illustration in this slide. Okay. These 5 are the ones, either you can just put one, or this is with a rotation, and this is with a mirror. This is which is a mirror which is perpendicular. Here it is a rotation and a mirror. So, essentially around a point, if you see, there are 5 are there point groups. Okay. And these are all the 5 types of crystal structures, just taking only point groups into consideration. If we add glide to it, there are 2 more will come. So, now total 7 space groups are possible in one-dimensional lattice, correct? Okay. There are various ways in which this representation of point groups can be done. In the table, if you look at international table, one is Hermann-Megwin. I had explained in detail, or Schoenfly symbol. Schoenfly symbol, I had not talked about it. Okay. That is used by spectroscopy people, but crystallography, we are more of we use more often Hermann-Megwin symbol. That I had explained in detail. Anyway, I will explain it briefly again here today. Okay. Then in a stereographic projection formalism also it could be represented. Then a matrix formalism which we could represent, which I had mentioned. Then our drawing of that actual crystals are showing the, for this itself could be either a drawing which is synthetic or a natural crystal. These are all the various ways in which it could be represented. Okay. These aspects of rotational symmetry in the matrix formulation, this is how we could do these aspects. In the, when we wanted to represent it in a stereogram, essentially what we do it is that we take the primitive circle, okay, on which these are all the coordinates, and then if we take one point on that circle, because this is for a 2-dimensional point, this gets since for a monoclinic structure, so twofold rotation, this will come here, again one more rotation it will come here. This is one way we can represent, or other is the twofold rotation is represented by this sort of a symbol. So these are all the two options, okay. Like mirror, this is one here, if you put a mirror this will get reflected here. So this is here only the symmetry is represented, here essentially one particular point, how it transforms or moves from one to the another position by the operation of the symmetry. This is for 2 mm, this for 4 mm. These are all the ways in which it is done. All the details which I had shown earlier, and that is available in all standard books which you can see. Okay. So this what we have considered so far is essentially what all the various ways in which the two-dimensional point groups can be represented in a stereographic projection. Okay. The same point groups can be represented, okay, in another way, just taking like a crystal that is asymmetric motif, and you show what is the operation of it, okay, what is the type of patterns if we see, okay, which exhibits, okay, or it is taken from an art which exhibit the whether one fold or two fold or mirror symmetry, all these, plus some crystals which exhibit or molecules which exhibit this sort of symmetry operations, that is shown in this. If you look at it here, it is one fold, mirror, 2, 3, 4, 5, 6, and then combinations of this, okay, rotation and so this brings out only 10 distinct ones, which I had already mentioned. Okay. Then I mentioned that if you add a glide, we will have a 17 will come into the picture. This is for an asymmetric motif, all the 17 types of crystal which can form, okay, the space groups which can come, that is shown here. Okay. And these are given in International Union of Crystallography, it is given as each space group is given a particular number. Okay. Once that number is known, you open that page in that book with that number, then they give the full symbol as well as the short symbol, what is the point group corresponding to it. All these informations are given in the table and the details which has been explained in the class. Okay. Similarly, three-dimensional point group also we can represent it in that same way. Okay. And here most of the time you find that these are represented in a stereographic form. Okay. In the stereographic projection, if you look at it, okay, for a four-fold rotation, you show the axis, okay, on a stereogram, and then take a motif at a general point and how it gets repeated itself, that is what shown. Or as I mentioned, you can show by the symmetry. Okay. So here all the symmetry elements, the 32 point groups are shown in these two slides, okay, which has been explained earlier. This can be given in many books. You will find that these are given in a table form also. Okay. In this table form, if you see it, the one which is shown with this color, okay, this essentially corresponds to what is the maximum symmetry which the crystal will exhibit. Okay. This is what the symmetry which a lattice exhibits. Okay, lattice exhibits the full symmetry, and this one, if you see it, are the ones which show what is the minimum symmetry which should be there. Okay. This is the minimum symmetry with which all this classification which has been put. Okay. All these details you had gone through, and in this table, if you look at it, when we say that 432, okay, what does this order 432 mean? Okay. So this is explained in this sort of a table what the primary number mean. Okay. For each of the crystal system, here it is a 0 1 zone axis, okay, along which that 2, when we the two-fold rotation comes, and here if you look at it, tetragonal 0 0 1 is along that C axis it comes. So what all types of symmetries which will be coming along which particular direction crystal structures, okay, that is how they are represented in this table, okay, in the Hermann-Megwin symbol. On this basis I had just shown the various crystal structures, okay, and their maximum symmetry elements which are there, okay. This I had already explained, okay. Now I mentioned that the space group is essentially nothing but a combination of point groups plus translational symmetry associated with it, all the point groups, okay. And on this basis, if the point group itself, if we look at it, we can say that whether it is a polar, okay, or it has got a center of symmetry. On this basis, we can tell polar will not have a center of symmetry, and then enantiomorphic or non-enantiomorphic, that will show optical activity, okay. So, ferroelectric material and piezoelectric material. So, various properties, the elastic properties, all these properties could be defined looking into which sort of crystal class. So, if you know the property, how it changes in different directions if it is measured, we can tell that this is the particular type of a crystal class in which the sample should fall into, okay. These are all the various symbols which are used to represent all the symmetry operations, okay. This I had explained in detail, okay. Now the space group also can be represented. What are the ways in which the space group could be represented? One is the Hermann-Megwin symbol could be used to represent the space group. So essentially what is being done in this is that what is the type of as the classification which I had mentioned, for depending upon the different directions, okay, for different crystals, how it is to be, how the first number, second number and the third number will come, okay. Then P, that is primitive, is represented as P, I for body centered, F for face centered, A, B, C, and then R for trigonal, okay. These sort of symbols will be put in front of it. That is how the full space group is represented in Hermann-Megwin symbol. Then just mentioning all the symmetry operations also that can be represented, okay. In the International Union of Crystallography table, all these representations in which the space group is represented. Another is we can show a symmetry diagram. What is essentially done is along any one of the axes, mainly along one of the principal axes which we use, along that axis show the unit cell, okay. Then show all the symmetry elements which are associated, that is one way. Or another way in which is done is that, like suppose it is going to be a rectangle, okay, this is going to be for a simple orthorhombic structure. Then we can either show all the symmetry elements, or you take a general point, okay. That general point means that one which does not have any symmetry associated with it. So you apply all the symmetry operations, it will generate all other points around that lattice point. We show that these are all the two ways in which it is represented, okay. The third is the fourth way in which it is represented is multiplicity which is associated with the different points, okay. Then Wyckoff letter, site symmetry and coordinates, because what happens is that when you represent with the symmetry elements, this point may have some symmetry associated with it, maybe the center has got some symmetry, okay. There are many points which does not have any symmetry associated. So there are some points which have some specific symmetry associated with that point in that unit cell, that decides how many atoms have to be placed in the unit cell is decided by that. All those informations are given, and each of these special points or general points are represented by the Wyckoff letter, and around each of these points adjacent neighbors, if we consider what sort of a site symmetry which it will have, that is also given. And then once that is decided how many points are there, what are the coordinates of that points, that is also mentioned, that sort of a table. This is the table which can be used to construct crystal structures, okay. So what is the way to understand this? This is the aspect which I will explain it a little bit in detail, okay. Here what I had considered is P4 mm, okay. That means that point group symmetry is 4 mm, okay. It is a tetragonal structure because that 4 is coming as the first letter, okay. Then 2 mirrors are coming, okay. Then then 99 means that sequence in which it is being mentioned, the 99 is the number corresponding to this for P4mm. For each 230, that 1 to 230 they are numbered. Okay. And then you look at this symmetry diagram. This is along C axis, is then BA and B axis. Okay. Then the unit cell is being shown. Then around each of the lattice points, okay, you consider this is the fourfold symmetry associated with it. And at the center also, as a consequence of fourfold symmetry comes, which I had explained how this happened. Then at this midpoint, okay, on each of these axes you have a twofold symmetry, special points are coming, and then these are all the mirror reflections which are coming, the mirror planes are shown. Then this is a glide plane which comes. Okay. In this, if we put a general point 1 here, by all these symmetry operations, this is where that all the symmetry operations, by doing the symmetry operation, we can generate all the other positions where they should come. So these are all the two information which is given, and where is that origin, this is the information. All these special points, if we consider, will have some coordinates associated with it. For each of the special points, the coordinates are given in this table form. And what is the side symmetry corresponding to it, that is given in this column. And that Wyckoff number is it starting from one having maximum symmetry, starting from the origin, it is being given A, B, C, D like this. And for example, if we put at a general point, for this particular one, essentially another 7 more points have to be generated, okay, which are dictated by symmetry, then only this completes this. When the motifs are placed around it like this, the unit cell, it will exhibit the 4mm symmetry, correct. Now at this central point, if you consider, if you have placed it, the central point also, if you look at it, these points are there, the same symmetry it will exhibit. Okay. If I wanted to place an atom at the center, okay, if I keep it here or here or here, okay, if I keep it at this one point which has been put, apply a translation, that is why it says the plus a translation. So this point gets repeated, that is how the full lattice is generated. Okay. Then only if you consider an atom like this ball, it has got an infinite symmetry. So all the symmetry elements it will have, we can keep it at this point, only one is required. Whereas if we keep at this one which has one fold symmetry, then we require 8. Like here, if we look at it, we have a twofold symmetry which is associated with it. Okay. Then we require a 2 points. Okay. Then we can keep along this mirror symmetry. Okay. Then what all points at which it has to be kept, all those coordinates are given here, where the atom should be there in the lattice. Okay. This is what this table essentially illustrates. Okay. So here what I have done, it is on this, that Wyckoff position, the letter which is being used, ABC, corresponding to which type of a symmetry element in the unit cell, this is what I had shown. But what is essentially important is that this same thing, as I mentioned, with respect to a 1A position, if I keep an atom here, here or here, it just satisfies. This way, now it has got a 4mm symmetry. Instead of it, I can put the same atom at this particular position, at half Z. Okay. Then also, if the lattice put unit cells together, this also satisfies 4mm symmetry. Here, if I put atoms at these points on the unit cell, like this, then we join all unit cells together adjacent to each other. This also satisfies the 4mm symmetry. If I put it on this particular one, on this mirror symmetry plane, then these are all the positions on which it will be put, and this also satisfies 4/4. So here, if you look at it, this is the way it has to be put. Here, this is the way, and no symmetry. If you put it, this is the way it will come. That means that given an atom, okay, these are all the options which are available for this crystal structure where that atom could be placed. If you place that atom like that, at any of these positions, irrespective of whichever be the position we have kept it, each of these unit cells satisfy the 4 symmetry. This is the first. So, the option which atom has got is these are all the possibilities. That is what that is why I said it is a geometrical crystallography. Okay. The next one which happens is that if we keep it at these positions, the number of atoms per lattice point turns out to be 1. If you keep it here also 1. If you keep it here, how many are required in the unit cell? We have 2. If you keep it here, in each unit cell we have 4. If you keep it here 4, here also 4, here also will be 8. Okay. Given an atom, suppose it chooses some particular choice which is dictated by some energetic considerations, which is beyond the scope to discuss in the class now. Then depending upon, suppose it has taken 4, that means that the density of the material will be changing depending upon the once the lattice parameter is fixed. So, you understand that. So, essentially, so this tells all the possibilities, and if it takes it this way, then immediately if you know the unit cell parameter, the number of atoms which are density, then you can find out that this is the type of position which it can occupy. We can infer some information about it, correct? Okay. Then and another one which is very important, only this aspect I will cover, is that suppose we consider a motif which is made up of an asymmetric motif which has got a, in this corresponding to this particular case, 4 symmetry, how it can be placed around this lattice point. Okay. Either we can keep it in this position, then it satisfies the 4 symmetry of the lattice, or we can keep it rotated by 45 degree, then for it satisfies. If I keep it at any other angle, rotated by any other angle, okay, like in this particular case, this does not satisfy the 4 symmetry. Now it will have only a 4-fold symmetry. Okay. Though this has got a 4 symmetry, the motif has got a 4 symmetry, the crystal also has, the lattice also has got a symmetry which is that same as that of a here, depending upon how we position it. So, essentially the symmetry which is shown by the crystal depends upon, if we keep a motif at a particular position, what all the symmetry elements which are associated with that position, consider it. What all the symmetry elements which the motif has got, whichever symmetry elements are coinciding, that is the symmetry element which the crystal will exhibit. You understand that? Suppose a motif has got a 1-fold symmetry, you put it around a square lattice which has a 4-fold symmetry, but motif have got 1-fold symmetry, then the crystal finally exhibits only a 1-fold symmetry. That is the example which he has shown in the first slide. Okay. So, this is one which is important. Okay. Then these aspects. Then the another aspect is that suppose the same type of an atom. The question which comes is that we said that these are the possibilities which are there. Can I keep that same atom at, for example, in this position and in this position? If I put the same type of an atom in these two positions, then the space group symmetry will change. So, it will no longer maintain symmetry. So, that is not possible. Okay. Suppose we have another type of an atom which is there. Okay, A type of an atom and a B type of an atom. A can be put here, B can be put here. So, that is possible, that is allowed. So, if we try to do it, then if we put A here and B here, then what will happen is that AB is the stoichiometry and the number of molecular formula is only 1, that is what it will be there. But the same molecular AB stoichiometry I can put it by putting one here and then another here. So, there are many combinations are possible. So, this decides what is the type of stoichiometry with which we can generate alloys, okay, when we have different type of species are given with which we are forming compounds. So, suppose it is say AB, okay, A and B. We can have AB composition, AB2, AB4. These are all the ones which are possible. Directly looking at it we can tell. Okay. The question which comes is that suppose this not what I am telling it as suppose, but it has been observed. Okay. That is a material with AB3 or AB5, is it possible to form? If you look at this position. Okay. In fact, if you ask me, I will tell that yes, it is possible. How exactly it is that in this A atom can be placed at this position 0 0 Z. Okay. What does Z means? That it is an arbitrary position which you can choose it. A is put, B can be put at 0 0 Z1, then that satisfies also again that same symmetry. C can be put at and another B atom can be put at another distance. Like this you can put it and form still having the same symmetry is being maintained. It is possible. Okay. In fact, this sort of things have been seen. So, because which type of a crystal structure it forms, it is dictated by the energetics. Okay. But if you look at this sort of a table, simply looking at the ratios, you find that it appears it is not possible. The only way it is possible is that this, what is essentially important is that suppose this turns out to be 0 0 0, putting one atom here, okay, you cannot put another atom in that position. Okay. Okay, that is what that question which I meant. Can a crystal have a structure and stoichiometry other than what is dictated by this table? Yes, it is possible. Okay. This is one example which I had given, one atom at the 0 0 Z. Okay. The other atom can be placed at 0 0 Z1. This also, both of them exhibit that 4-fold symmetry, okay, 4 mm symmetry will be there, or A atom here, B atom here, okay, or if you look here, this is 4 A atoms, okay, another atoms. Okay. This also has got an AB stoichiometry, but it is A4 But what is going to happen is that depending upon the number of atoms, the density, if the Lattice parameter remains the same, the density will change. This is the same which is for AB2 stoichiometry. These are all the possibilities which we are showing. Okay. These are all the various possibilities. Okay. Okay. So, from this what we can understand, any type of a composition can be obtained. Okay. For any type of a composition, a particular crystal structure it can form if energetics permit. But the type of crystal structures which is possible is fixed to 230. Okay. So, if we consider between the various types of crystal classes, from a hexagonal, okay, suppose a phase transformation, this is called as a hierarchy, that is a disordered state has got the maximum space group, okay, maximum symmetry operations which are possible. From this, when a phase transformation takes place, it undergoes a transformation, there will be a lowering of the structures. So, if it takes place by a replacive transformation, okay, then what are the types of structures to which it forms? Hexagonal, when it transforms, it can go to orthorhombic. Hexagonal, by a phase transformation, it can't go to cubic. What I mean is that this is a square type of a lattice which is corresponding to a cubic. If I put an A atom at some particular position and B atom at some particular position, I can generate, okay, like if this is a cubic lattice which is a representation, if I take it like this, A atom and B atom here, and the C is at this particular height it comes, then it becomes a tetragonal structure, but it cannot be made into a hexagonal. By replacement of atoms among the sites, when a diffusional transformation occurs, where atom sites, one atom goes and replaces to another site, such transformations from cubic it will go to tetragonal, okay, or cubic to trigonal it can go, or to monoclinic or triclinic, hexagonal to orthorhombic to monoclinic to this one. These are all the way in which transformation. This also tells that in a replacement transformation what are the types of structures which can be formed, okay, when a phase transformation is occurring. But these are all diffusional transformations. Non-diffusional transformations, which are essentially called displacive type of transformation, there by deforming a crystal one homogeneously, you can go from one particular structure to another structure, it is possible. That is what the morphostatic transformation, because in a morphostatic transformation FCC can be made into HCP, that is cubic to this one without introducing a defect, correct, that transformation is occurring. But hexagonal to cubic, if you have to go without introducing defect or a stacking fault, normally you can't undergo this transformation. Whereas by deforming structures, okay, from one structure to another structure, it is always possible to make, like BCC. BCC can be transforms into hexagonal, okay, but cubic to this transformation generally here by this rule, if you consider, it is not possible, but monazite it does occur. Essentially what we do, we compress it like this, displace it like this, all directions, different directions, you give different displacement, but you can change it to another structure. So that is non-diffusional, or that is called as displacive transformation, okay. So everywhere crystallography plays a lot of role in understanding, okay. Then depending upon the which type of a structure which is there, whether it is primitive, okay, that is among the classes of crystal structures which are, all the crystals, the 14 Bravais lattices could be represented in frames of primitive unit cell, okay, but some of them are non-primitive unit cells are used to represent them, because these non-primitive unit cells represent the full symmetry of the lattice. That is the consideration which is used to represent that way. So when we do that, different lattice points which are there in the unit cell, they will be represented in fractional coordinates. So corresponding to each of them, what is the sort of fractional coordinates which will be used, that is given in this table, okay. Generally in any of the crystal data book, if you look at it, how do they represent the different materials, okay, all the crystallographic information. For example, if you take copper, it is given copper, A1 is what it is called a structure Bareilles symbol, okay. This is not a one which is used in International Union of Crystallography because International Union of Crystallography, if we use it for copper, we use FM3 bar M, and it is better to learn to start using that. Then FCC is that mentioned full, and then the structure is generally this is a simple cube, it is a cubic structure. In the cubic structure, what is the lattice parameter, and Z means that if it is a cubic structure, if it is FCC, you can say that around each lattice point there should be 4, so the number of atoms which has to be there is 4. This is the space group and atom positions at 4A, because this is taken from the crystallography table. These are all the positions which the atoms will occupy. That is, if we have a particular atom, and as we have seen in the case of P4mm, okay, if out of all the choices, if only one particular element is there, which one it will choose? Generally it will choose the one, okay, where the site exhibits maximum symmetry, okay. Then if it chooses that, okay, that is only at one position, so the number of atoms per unit cell is going to be 1, that is one. And generally whichever site has got maximum symmetry, that always has got the energetically, it has got the minimum and lower energy level. So these two are related also, structure and symmetry are quite related topics, okay. Similarly tungsten, which is body centered, the same way you can say atom positions, but Z equals 2, okay. Similarly if you look at it, graphite or sodium chloride, for example, if you consider, that's it is a sodium and chlorine is there. Here if you see it, sodium atom occupies, here the positions are 0 0 0, half of 0, that means that this position is a fixed special position. Here only one atom can occupy one position. we consider the case where 0 0 Z is there, one atom, and another atom can have at a position Z with different value. That is not possible here. That is why here one position is occupied, next interstitial site the next atom position comes, like that it goes. But when you go to higher interstices where these positions which are given by mirror symmetry, where the value x comes, then there are many atoms can occupy along those lines. Okay, that will. Okay. Okay. Similarly for zinc blende, and here if you see that Z is given 4 because 4 NaCl, that is 4 of sodium and 4 of chlorine. So, NaCl as stoichiometry if you consider it, only 4 is going to be there. This is how similarly for zinc blende it is going to be Z equals 4. This way we can understand. Okay. This is one way of representation. Another way in which it is represented is called the Pearson symbol, which is being used. In that, triclinic is represented by anorthic, so it is represented A, monoclinic is M, orthorhombic is O, tetragonal T, trigonal H, okay, hexagonal H, okay, and cubic is C, and then whether it is a primitive or body centered, so those symbols are used. Okay. Then N represents what is going to be the total number of atoms which are present in the unit cell. Okay. This is another way of representation. So, for copper if we have to represent it, we will put CF4 it will come. Okay. Suppose we have to represent diamond, it will be CF8 it will become. Okay. Then if you see the books, there are various types of symbols which has been used. So, this is the symbol which is used by International Union of Crystallographers. Then we use another BCC, BCT, all these used to represent crystal structures. Then the Schoenfly symbols are used because the Schoenfly symbols and the point group symbols have got 1-to-1 correspondence. Okay. But as far as the space group is concerned, the Schoenfly's, when he formulated this, independently found out what he did was that depending upon which crystal which he determined, he gave the number, after giving this he gave number 1, 2, 3 like that, which was arbitrary. That is why it is better to use, crystallographers prefer this one, and chemists, especially people who work on spectroscopy, prefer this because this directly tells, because they look at what is the molecule, what is the vibrational spectrum, what is the rotational spectrum, for which it is essentially a point group which is more important rather than the space group. So, they use this. Okay. Then another symbol which is structure barite which was developed, this is what all the more confusing, A1, A2, A3, A4, these are all there, but I think logically explaining how it has come is going to be very difficult. Here there is some logic is there. So, it is better one starts using this sort of symbols to represent crystal structures. Okay. Because if you represent it this way, then immediately you can go to International Union of Crystallography table, look at that specific number, all the information, atom positions, everything is available. Okay. So, here it is for a primitive cubic. Okay. Like up to this position, if you see, if an atom is put at this position, only one atom can be put, the next atom has to, if comes, next type of an species, it has to be put here or here or here. But if I like here, okay, I can put one atom at this position, x, x, this one. This x is a variable number. One more atom can be put with a value of x which is different. So, that is possible only for these. That is, suppose like here if you consider general position, if I put 48 positions are there. Okay. What I can do it is that I can put A atom which occupies a general position. Since in this unit cell this is one general point, at this general point I can put a, suppose A atom has been kept here, B atom is kept here, then by symmetry elements I will be generating all other ones, like this I can put it. Okay. In another position B atom can be again put in a general point, Again by symmetry, that is still it is space filling, nothing is touching each other. By symmetry operations, if you consider this way also, atoms can be placed in the unit cell if energetic demands. That is what I wanted to tell. Okay. Here I am just showing the structures based on taking on a simple case of a sodium chloride. Here if you see it, that is sodium atom, assume that it occupies this position, because here it is fixed. So, only one atom can come. Any other position if you consider it as a different symmetry. So, the next atom which it has to occupy, either it has to go to this or this position, because from the energetic consideration this is how it happens. Okay. But it is by a reflection it comes, there are many options are available. That is why in those positions, though the crystallography table says that this is the value of x, we have to do X-ray diffraction and do the intensity of the peak. Okay. From that we can find out what is the value of x. That is what all the crystallography is about. That is, the whole X-ray crystallography is to find out not only the crystal structures, but also what is the specific position which each atom is occupying. That value x in the table is not defined. So, it is the job of the crystallographers to find out what the value is. This will vary from element to element. Okay. In one element, that value of x could be some particular value, 0.3, another it could be some 0.35, okay, another element when it forms the same crystal structure. So, that is how it changes. Okay. So, similarly, like zinc sulphide I have taken, here also you can see that this is the way that the zinc atoms, they occupy some specific positions. So, the sulfur atoms will occupy that 4C position, and when the number of atom increases, if you wanted to look at the unit cell, it becomes quite difficult to understand it. What is the best way in which it can be done? Is take one atom, what are the nearest neighbors which are going to be there, like this sort of a cage, and instead of showing the atom position, now with these cages you can construct it, it becomes much simpler to understand the crystal structure. This is one way in which the crystals are represented. All these aspects have been covered in their classes, and then in addition to it, what all the, for a given a particular plane, how the directions have to be represented, how the planes have to be represented. If two planes are there, what is the direction which is common to it. Okay. If two directions are there, what is the plane which is common to it, what is zone axis, all these aspects have been covered. So, essentially what I have done it is some aspects of crystallography which has been covered over the course of 7 or 8 lectures. I had just tried to highlight these aspects of it. Okay. Anyway, I hope I had given overall idea, okay, all various aspects which I consider is important in electron diffraction and imaging. Okay. So, the examination is there shortly, go through it and prepare. Okay. Wish you all success. Thank you.